Hello, everyone. I would like to thank the organizer for giving me an opportunity to give a presentation on this special occasion, which I think will be well remembered in the history of the workshop. This presentation covers two separate but related subjects, neuromorphic computing and compact modeling. To begin with, let's look at why we care about neuromorphic computing. Well, there are many reasons for it, which has been covered in many talks that you can refer to. So I do not want to repeat them. Some of the key features of neuromorphic hardware are listed in this slide. The most important one is about power consumption. Compared with the existing computing systems, our brain can work at much more than 1,000 times lower energy and can be more efficient in many tasks. While neuromorphic computing is very hot today, I found that a lot of people are confused about the concept of neuromorphic computing and mix it with artificial intelligence and machine learning performed by deep neural network. Their differences can be illustrated in this slide here. Some common AI applications in deep neural network include image recognition with convolutional neural network and speech recognition using recurrent neural network. In both cases, all data are represented by numbers as input and being presented to the network at the same time. This requires a high volume of data processing, and the computation is usually performed by GPUs. Neuromorphic computing, on the other hand, mimics our brain to process data encoded as pulses in the time domain. This kind of hardware is usually referred to as spiked neural network or SNN. The spikes in SNN can be very sparse, and therefore it can be much more energy efficient. A more detailed comparison between deep neural network and neuromorphic computing is given in this table. Deep neural network is more mathematical based, and the data coding is usually performed in the voltage domain. On the other hand, neuromorphic hardware is more biological oriented and processes data in the time domain. The most important advantage of neuromorphic hardware is power consumption due to the sparsity of the pulses. It is just like our brain can rely on food to function and is always on. In terms of functionality, deep neural network mainly learns through training, as in supervised learning. Neuromorphic hardware tends to learn by itself, such as in unsupervised learning tasks. The corresponding model for the two different kinds of computing approaches are given here. Deep neural network takes digital number as input and output another digital number, while spiked neural network has asynchronized pulses as input and output a pulse at a particular time. Therefore, to model neuromorphic hardware means that we have to model a neuron. It consists of the cell body that holds the nucleus. Connected to it are many dendrites to receive signals from other neurons. These signals will excite this particular neuron to generate a pulse that passes through the axons, connecting the dendrites of other neurons through the synapse. The action in the synapse is quite complicated, that composed of electrical signal transductions as well as chemical reactions. To simplify the modeling task, we usually just assume an electrical pulse is being transmitted through the synapse between neurons. The specific action that takes place in a neuron is called the spike timing dependent plasticity, or STDP. It explains the effect of the relative timing between the input and output. If the output comes after the input, we can say that the input is causing the output, following a causal relationship. This is the normal response and will be encouraged by increasing the internal potential of the neuron for faster response. This process is called long-term potentiation, or LTP. In the opposite case that the output of a neuron comes before the input, the output pulse can be considered as a forced pulse generation and should be depressed. The process is called long-term depression, or LTD. Through the LTP and LTD process, the neuron or synapse weight is modified to make it fire more frequently or suppressing it from firing. The output of a neuron will be a train of pulses with information coded in the time domain. The action of a neuron is like a memory device that keeps track of the history of all the input pulses. To model a neuron, we can refer to how memory devices are modeled in spikes. In the literature, there are many papers about compact modeling of memory devices. I've listed some here. However, when I look for memory models available in commercial spikes, it is difficult to find one. For example, here is the list of models I found in HBytes, and there is no model associated with memories. I also go through the website of compact model coalitions, and I do not see any existing standard memory model, or any plan to include a standard memory model in the near future. I guess one reason is that advanced memory device structures are not mature, and it is difficult to develop any standard model that fits the ever-changing material systems and device structures at this stage. At the same time, memory devices have some special characteristics that are quite different from the traditional devices that we have been modeling. Let's take a look at the characteristics of the devices we have been modeling. I've collected a list of devices we found in spikes today, which includes passive elements, voltage and current sources, transistors, etc. A typical input deck of a device in spikes is given here. For this device, the characteristics is determined by the model parameters that govern the device physics, and the insert parameters that describe the structure of the individual device. All these parameters are only input parameters that remain constant over the entire simulation. And the model will calculate the currents with the given parameters when the terminal voltages are provided. The differences between memory devices and traditional devices can be more easily seen by looking at their current voltage characteristics. For a two-terminal device, such as the resistor, it has a one-to-one correspondence between the current and voltage. Active devices, such as PN diodes, can be regarded as nonlinear resistors. The same one-to-one correspondence between current and voltage is also observed. For a two-terminal memory device that we often call a memristor, the current is not only dependent on the current voltage input, but also the previous history. It leads to common behavior like hysteresis that characterize the different memory states and the switching between the different states after reaching a critical voltage. In some cases, like flashing memory, snapback characteristics may also be observed. These kind of behaviors do not appear in traditional devices. To implement a compact model for traditional devices, we usually use the quasi-static approach. Taking a MOSFET for example, if the MOSFET only has external terminals, the current is uniquely defined by the given set of fixed parameters and the input terminal voltages at the given time. Because the currents are expressed only in terms of terminal voltages, and the device parameters remain constant, the output currents will take up constant values if the input voltages are fixed over time. However, it is not the case for a memory device. It is because a constant voltage may result in the accumulation of energy over time and eventually change the structure of the device. For example, in an RM, a filament can be formed when a given voltage is applied for a long enough time. The change in device structure will lead to a change in the terminal current even though the input voltage remains unchanged. In traditional memory modeling, it is also common that the states of the memories are modeled by a digital switch between two different states. For the purpose of neuromorphic computing that requires analog memory, it becomes necessary to handle memory elements with different resistance states, which are controlled by terminal voltages, as well as the time of the bias being applied. So, how to properly model the memory characteristics? We know that traditional devices are memoryless, and the terminal current voltage relationship can be expressed with the equation given here. For a memory device, the instantaneous current depends on both the instantaneous voltage input as well as the history of all the previous voltages. Therefore, we need a new state variable to keep track of the current status of the device. The state variable will be a function of the previous state at its immediate past, plus the instantaneous voltage input as shown here. Or in the form of differential equation, it can be expressed as the rate of change of the state variable is given by its current state plus the instantaneous input voltages. Once the state variable is calculated, it is incorporated in the current voltage equations to calculate the instantaneous currents. T.C. Wang and J.G. Rochefoucauld of UC Berkeley have given a very detailed explanation on the required behavior of the state variable, and you may read the paper listed here if you are interested. Implementing a time-dependent internal state variable is not new, and is usually done by a subcircuit to create an internal node to keep track of certain state. The most common one is to keep track of the internal device temperature in the self-heating process. Similar approach can be applied to memory devices. Let's take a RAM model for example. In a RAM, the memory function is usually explained by the formation of filament due to oxygen vacancy in the device. The current through the RAM is dependent on the size of the gap between the filament and one of the electrodes. By using the gap size as a structural parameter, the current has been expressed by the gap size and the applied voltage. Here, I took a model developed by Stanford to show how the RAM current is expressed in terms of gap size and input voltage. The gap size is given by a differential equation, which is a function of the existing gap size and applied voltage. The differential equations can be implemented by a subcircuit here, and the SPICE engine will keep track of the value and convergence of the state variable. One drawback for such approach is the additional node causes one extra circuit equation that enlarges the Jacobian matrix. As a result, it will increase the time for SPICE to solve the matrix equations. The hysteresis behavior in a memory device can be achieved by selecting a proper function for the state variable. For example, we can pick the rate of change of the gap size to be a cubic function of itself, following the approach proposed by Tenshu Wang in the reference. In the DC case, the gap size will not be changing with time, and the dG over dt term becomes 0. Then, we can plot the relationship between the gap size and the voltage following the cubic function, which is given here. We can see that the two sides of the graph, G has a well-defined value for any given voltage. However, in the middle region close to V equals to 0, G can take up multiple values, and the choice is determined by the initial value used in the iteration process. Now, let's assume that the memory device is being swept from the left. Initially, there is a one-to-one correspondence between the voltage and the gap size. As a result, the value of G is well defined. Once the voltage enters the multiple value region for G, the value of G is determined by both the previous gap size and the newly input voltage. The previous value of G will act as the initial guess of the iteration process to find a solution. As governed by the previous value of G, the solution will follow the curve as shown here until it leaves the region for multiple value of G. With a new voltage input to the right side of the graph, there will again be only one G value that matches the given voltage. A sudden change of the G value will be observed. Then, G will follow the remaining part of the curve when the voltage sweep continues with more positive value. When sweeping the voltage from the right, similar mechanism will guide the behavior of G to follow the upper part of the curve as shown here, to move past the multiple G value region. Then, a sudden change of G occurs, so that it moves to the lower branch of the curve when the value of the voltage enters the left side of the graph with one-to-one correspondence between the value of G and the input voltage. After that, the curve will continue to the end of the graph with further reduction of voltage towards more negative value. The hysteresis behavior is correctly observed. With the gap size defined, the current can be modeled by the equation given here. The hyperbolic tangent function will return a value close to either -1 or 1, except for the transition region. This means the current will either have a value of V over R or 0, depends on the size of the gap. And the resulting current voltage characteristic is shown here in the figure, which agree well with most of the reported behavior from experimental results. Subcircuit is a common way to implement state variables. However, subcircuit increases the circuit matrix size and slows down the simulation. There is another way to include the state variable using dynamic parameters. As mentioned earlier, both the instant parameters and model parameters in SPICE are mainly used for input only. But we can also allow the instant parameter to be a dynamic parameter that can be updated over time. As the instant parameter usually represents the physical structure of the device, using the instant parameter to keep track of the structural change of the device is intuitively correct. To update the instant parameter, it has to be written in an incremental form, such as the new gap size is equal to the previous gap size plus a delta G. Using the internal time step in SPICE, delta G can be calculated using a function call to the numerical integration routine provided in SPICE. For example, if backward Euler is used as the integration method, delta G will be given by the equation here. By calling the proper integration function in SPICE, it is going to produce the same results as in the case of the subcircuit approach. Using the dynamic parameter, a simpler approach can be used to implement the hysteresis behavior directly. Here, we can use a step-like function, such as the Fermi-Dirac or hyperbolic tangent, to define the two sides of the hysteresis loop. For example, we use the Fermi-Dirac function to define the curve S low that switches at the voltage V low, and S high that switches at the voltage V high respectively. This is shown in this graph here. Now, we can define the state variable as shown in this equation, which also depends on its current value and the two functions defined earlier. The behavior of the state variable can be explained like this. When scanning from the left, S is close to 0, so the first term of the equations becomes very small, and S of V mainly follow the curve S high. Similarly, if it starts from the right, S of V is close to 1, and the second terms become very small due to the 1 minus S term. And the curve will mainly follow the S low curve. This produces the hysteresis loop with the separation determined by the value of V low and V high directly. We can directly compare the performance of state variables implemented by different methods. The graph here shows the simulation results of a memory array using the subcircuit approach and the dynamic parameter approach. When the dynamic parameter approach is used, we can call different integration functions within SPICE to obtain the increment. So, we also included data from the backward Euler integrations and the trapezoidal rule integrations. The total number of nodes using the dynamic parameter approach is only about 12% less, because all the driving circuits are included in the simulations, and the size of the memory array is relatively small. Comparing with the subcircuit approach, the dynamic parameter approach with backward Euler integration reduces the transient simulation time by about 17%. It is mainly due to the smaller circuit matrix size, so that SPICE can obtain the circuit solutions more efficiently. When the trapezoidal rule is used to perform the integrations, the simulation time is further reduced by about 50%. It is mainly because the trapezoidal rule integrations lead to faster convergence that results in a smaller number of iterations. Here, I would like to draw your attention that SPICE checks for convergence of all state variables when it is implemented as a subcircuit. But it does not check the convergence of the dynamic parameter. It usually does not affect the overall convergence in a practical circuit, as the behavior of the device is only observed from the external terminals. But we have to pay more attention when a small change in the internal state variable can lead to a rapid and unbounded change of the variables associated with the external nodes. RAM is actually a relatively simple device that can be modeled by using only one internal state variable. Many other memory devices may require more than one internal state variable to capture the correct physical behavior. For example, a floating-gate flash memory cell usually requires two state variables to keep track of the floating-gate charge and the threshold voltage of the device. In flash memory, there are as many as four internal state variables to keep track of the instantaneous temperature, the size of the active region, the crystal fraction of the amorphous region, and the existence of the dynamic filament. Using the subcircuit approach to implement such device will lead to significant increase in simulation time. As people are more familiar to implement state variables using the subcircuit approach, we have developed a more generic way to convert a subcircuit model to a dynamic parameter model so that the number of internal nodes can be reduced. To do that, we first look at the effects of an internal node. We use the temperature node in the self-heating model to illustrate its effects, as it is the most common subcircuit used in both traditional transistors as well as flash memory. The temperature node creates a new entry to the Jacobian matrix in the circuit equations as shown in this slide. As the internal node is usually quite isolated from other terminals, the rows and columns associated to these internal nodes are usually zero. By noticing this, we can actually take out this equation from the matrix and explicitly calculate the next prediction of the temperature value at the I+1th iterations without going through the matrix. By doing so, it preserves the size of the Jacobian matrix and reduces the simulation time. The extra linear equation due to the internal node can be solved explicitly using the original entries to the Jacobian matrix. And these entries have to be calculated anyway. Either you use spikes to obtain the I+1th iterations of the temperature value by solving the matrix equations, or you calculate the next iterative temperature value directly inside the model. Fortunately, the entries to the Jacobian matrix can be obtained easily by a function call to the spikes numerical integration method. For example, when a backward-Euler integration method is used, the actual equation used to calculate the temperature increment at the I+1 iterations is given by the expression here. The flowchart here illustrates the approach to calculate the temperature by including it in the circuit matrix versus direct evaluation in the model. In the conventional approach, as shown in the flowchart on the left, the computer makes a guess after the nth iterations for both the terminal voltages and the temperature, as they are treated the same way. Based on the input, the model calculates the currents and their derivatives. All the currents, voltages, and derivatives are entered into the Jacobian matrix, and that spikes to calculate the next voltages and temperatures as a result of the iteration process. In the direct evaluation approach, as shown in the flowchart on the right, the same temperature and voltages at the nth iterations are presented to the model. The model then calculates the currents based on the input. After that, the next iterative solution for the temperature is calculated explicitly based on the input voltages, temperature, and calculated currents without going through the matrix iteration. Then, the calculated currents, their derivatives, and the voltages at the nth iterations are entered into the Jacobian matrix for the next iterations to obtain the new voltages after the n+1th iteration. In this case, the equations to calculate the temperature is not included in the Jacobian matrix, as it has been explicitly calculated already. Therefore, the size of the Jacobian matrix becomes smaller, and the time to solve the matrix becomes shorter. At the end of the process, the values of all voltages and temperature after the n+1th iterations are obtained and ready for the next iteration. The accuracy when comparing the two different approaches is given here. You may ignore the data for PT in this graph, as it is irrelevant to this presentation. SC in the graph corresponds to the subcircuit implementation, and dE corresponds to the direct parameter evaluation. The calculated internal temperatures in both cases are exactly the same, as the same equation is used. The simulation speed is indicated in the graph below. The first data point is the case with self-heating is turned off. This serves as a reference for the simulation time. With the internal temperature is included using the subcircuit method, the simulation time is increased by about 50%, while the direct parameter evaluation method only slightly increased the matrix solution time. We can also compare the number of iterations, and the data shows that the number of iterations is only slightly increased when self-heating is included. The increase is within 2% from 50,000 to below 51,000 times. This is within the error margins of the iterations method. Another property that often occurs in memory devices is the snapback behavior. It can be found during the phase transitions in a phase's memory when a voltage is applied to it. However, when a DC source is applied to the memory cell, the voltage across the device is fixed, and snapback will not happen. In reality, there is always a resistor connected in series to the memory device. In this case, the final current and voltage of the device is related by the load line and the state of the memory cell. When the memory is at the high resistance state, the device will settle at point B in the graph. Similarly, it will settle at point A when the memory is at the low resistance state. In the switching process, the snapback occurs, which is governed by the abruptness of the switching of the state variable. Therefore, the snapback behavior is automatically handled by properly modeling the internal state variable. We can also look at the simulation results when different load resistance, Rs, is placed in series with the memory. When Rs is 0, it corresponds to the DC case we studied before. The memory directly jumps to the other state at the same voltage without snapback. When Rs increases, the slope of the load line is reduced, and the snapback behavior becomes more obvious. Another problem for modeling memory devices is the parameter extraction process. Normally, a fixed bias is applied to the device, and the change of some of the observable outputs are monitored over time to extract some of the time-related parameters or state variables. The bias voltage can be changed, but it remains constant when the time evolution is being characterized. In the example given here, I simply model the gap size of a RM to be an exponential function with time, and the rate of change of the gap size is governed by the bias voltage. But the programming of a memory cell usually involves different voltages applied to the memory cell at different times. So we have a problem on how to combine the data extracted at a fixed voltage to map it to the process of incremental update when a dynamic voltage switching is applied to the memory. Let's look at the following example, again using the previous simplified RM characteristics. When the voltage across the RM is increased from V1 to V2 to V3, how to model the change of the gap size? If we simply follow the time point in the simulation, G will follow the property at low bias in the first period, and then move to the curve corresponding to the constant bias at V1. The same process continues, and G will switch to the curve measured at V2 and V3. As G is updated by an incremental value during simulation, these curve segments are considered as incremental changes, and being combined together by matching the value of the gap size from the previous simulation period. The effective change of the gap size over time will be like what is given in the graph here. But obviously, it is incorrect, because the initial condition when applying the equations for G at V1, V2, and V3 are incorrect. The proper way to combine the static characteristics will be described here. When the bias voltage is switched from 0 to V1, It should correspond to the beginning of the static G versus time curve bias at V1, because it has not been programmed yet. So the initial gap size should be 0. In the second period, G will increase following the curve at V1 bias. At the time when the input switched to V2, it has reached a gap size G1 due to programming by V1. It should start to follow the V2 curve at the point where G equal to G1. Effectively, we have shifted the G versus time curve measured at V2 to the right until it matches the G value at the end of the V1 programming period. Similarly, when V bias is switched to V3, the G versus time curve at V3 needs to be shifted to the right to match the G value at the end of the previous bias period before it is used. After combining the curves this way, the characteristics of G versus time is given in the last graph here. To implement the model in spikes using the parameters extracted under static bias, an equivalent time concept is introduced. Suppose a train of voltage steps is applied to the memory cell. At the same time, the different rate of change of G at the different bias voltages are characterized, which are labeled as delta G1 to delta G4 in the bottom graph. In the beginning, when V1 is applied, G will change according to the delta G1 curve. At the end of the first delta T period, G has reached a value of G1. Before switching to the delta G2 curve, we have to calculate the equivalent time when the delta G2 curve produces the same gap size. After this equivalent time is deduced, the gap size will further increase following the delta G2 curve starting at the first equivalent time for the same duration of delta T. The same process will be followed when switching to the other biasing conditions. In this case, another dynamic state variable called the equivalent time is introduced. With all the basic components developed, we will apply them to model a PCM cell and use it to simulate a neuromorphic array. We choose PCM here because there are more data available for PCM-based neuromorphic hardware using spike neural network. In a biological neuron, the synaptic plasticity modifies the action potential of a neuron. In a PCM circuit, a train of pulses will change the PCM resistance. From experimental data, a train of high voltage pulses increases the resistance of the PCM cell due to the reset process. And a train of lower voltage pulses reduces the PCM resistance due to the crystallization mechanism. Using the dynamic state variables, we can model the gradual reductions of the conductance with high voltage pulses. And physically, it is explained by the increase of the radius of the amorphous region. Modeling of reduction of resistance is relatively easy, and you may refer to the reference at the bottom of the page if you are interested. The property of a PCM model developed in our earlier work is described here. 4 internal state variables are used in the model, which are the cell temperature, the crystal fraction, the active region radius, and the filament resistance. The first graph shows the input set voltage and reset voltage at a different time. The second graph shows the voltage appears across the PCM cell. The third curve shows the crystal fractions of the active region. The fourth graph indicates the formation of the filament that is responsible for the snapback behavior. And finally, the last graph shows the resistance of the PCM cell. It shows that after the set process, the PCM cell is set to the low resistance state, and the reset process restores the high resistance. The implementation of the neuromorphic hardware is a bit complicated. A circuit demonstrated by IBM will be used to explain the concept. The picture shows the operation of a synapse, which can be divided into 2 different stages. It starts with the leakage integration and fire, or LIF mode, that mimic the process of a pulse is received. And then it will enter the STDP mode to modify the weight of the synapse. In the LIF mode, VCAP is charged up by the leak resistor, When a pulse is received, M2 is turned on, and VCAP is discharged. Depends on the initial resistance of the PCM cell and the frequency of the pulses, the circuit will fire if VCAP drops below VTH. This is the basic operation of the LIF mode. The input pulse also triggers the generation of a specific STDP waveform that controls the amount of M1 turn on for the upcoming STDP action. After the neuron fire, the fired pulse is passed back to the synapse after some delay to compare its relative timing with the input pulse. The STDP process reprograms the PCM cell depends on the relative timing between the input pulse and the feedback pulse. It is controlled by the shape of the STDP waveform, which is indicated by the red line here. If the return pulse comes earlier than T delay, this pulse is fired before the input. This is the acausal case. With the timing of the STDP pulse, M1 is strongly turned on, and a high voltage will appear across the PCM cell. This causes a reset operation to increase the resistance of the PCM cell. If the fire is after the current input, the feedback pulse will arrive after the T delay period and fall onto the right-hand side of the STDP pulse. In this case, M1 is only weakly turned on due to the lower gate voltage, and a smaller voltage will appear across the PCM memory. This will serve as a sad pulse to reduce the resistance to mimic the LTP process. This graph provides a more detailed explanation of the timing relationship between the input and the output of the synapse. In the case for the LTP, the synaptic input starts the process. Together with the input pulse, the STDP waveform is generated. The pulse causes VCAP to discharge to below VTH, causing the neuron to fire. When the neuron fires, the signal is passed to the next neuron immediately. And after some delay, a pulse is generated as feedback to the current synapse. As it is in the low voltage zone of the STDP waveform, M1 is only partially turned on. Therefore, only a low voltage appears across the PCM memory to set its resistance. In the LTD process, the neuron fires before the synaptic input arrives. This pulse will be passed to the next neuron immediately. After some delay, it causes a feedback pulse to turn on M1. At the same time, the input pulse from the synapse arrived after the neuron is fired. As the input pulse arrived late, the feedback pulse will appear in the first half of the STDP waveform generated. Due to the high voltage of the STDP pulse, M1 is strongly turned on, and a high reset voltage is applied to the PCM cell to increase its resistance. To check if the model can match the data of a PCM cell, or more generally a neuron, we first calibrate our model with experimental data. Our collaborator, Dr. Chong Lam from IBM, has characterized the behavior of PCM cell and compared it with the behavior of a biological neuron. Pretty good match has been achieved by properly designing the STDP pulse waveform. And we have compared our model with the IBM circuit data as shown in the graph here. It shows that the model is able to capture the dynamic STDP behavior of a neuron. It means that the model can be used to simulate spiked neural network circuits with the data coded in the time domain. The construction of a neuromorphic circuit array consists of a few neurons with many synapses is shown here. We will use this circuit to perform a classification task in an unsupervised learning mode. The number of neurons depends on the categories you want to classify. For example, if you want a neuron to classify images of 10 numerical digits, 10 neurons will be needed. The simulation process is given in the flowchart here. The number of synapses in the array depends on the amount of data. Here, we use a 7x7 image to represent different digits in the number system. So, each neuron will be connected by 49 synapses. Each corresponds to the input from 1 pixel. Before passing the image into the array, the 2D images have to be converted into 1D arrays to line up with the corresponding synapse. And then, the value of each pixel is encoded into pulses in the time domain before sending the synapses into the neuromorphic array. This slide shows the simulation results when two artificial neurons are used to classify the digits 0 and 1 in a binary system. Starting with random weights for the synapses in both neurons, an image of a digital 0 is passed to the circuit. The synapses in neuron 1 picks up the information and adjusts the weights accordingly. Once neuron 1 picks up the data, neuron 2 is not responding. After that, an image of a digit 1 is passed to the circuit. As the weight of the image is closer to that of neuron 2 picks up the data. It then adjusts the weights of all synapses connected to it to represent the digit 1. As neuron 2 picks up the data this time, neuron 1 is not affected. After training, neuron 1 will pick up the digit 0 and neuron 2 will pick up the digit 1. The model has successfully demonstrated the capability of the network to perform self-classifications of some numeric digits without supervision. It is about time to stop, and here is the summary of the presentation. I have presented some basic components and techniques to model memory devices. And we have also demonstrated the use of such model to simulate some basic neuromorphic hardware. However, the difficult part is really in the parameter extraction. In traditional devices, we have put our focus to model the terminal currents of a device with respect to terminal voltages. Less attention has been paid on the timing dynamic of the device. And timing is usually only handled by delays as a result of terminal charge and capacitance models. But in neuromorphic computing, the detailed characteristics of the device behavior in the time domain becomes very important. And we do not have much experience on how to deal with such problems. It is a challenge for us, but also open up new opportunities for us to make another major breakthrough. Thank you very much.